Hello, everybody, to the new AOT Bonn, the April version, and I wish you a very warm welcome wherever you are in the world right now. And it's a warm welcome, at least from Bonn, because we finally get something what I call decent temperatures. So I'm really looking forward to the event today because I'm happy just because the weather is nice outside. As always, if you're here live, please interact with us in the chat. All the questions you may have for the speakers will be forwarded by our glorious moderator, Felix. And if there are more questions than we can possibly answer during the time that he has, we can always answer them in the chat for you, even if it's later, or you drop us an email or whatever, or Instagram, all these other social media that are out there. As always, we have a quiz for you. It's the April quiz edition, and you can find the link in the chat. I know that for sure. So maybe you click on that. Maybe you know some of the answers. You only need half of them right. And at least the click is worth it because you see some very famous astronomers for the last question. And I'm particularly proud of these specific questions. We thank our sponsors, the Tai Chi Zentrum here in Bonn and the SFB 956 for helping us with sending you all the prizes every month and the organization for that. Today, I'm more than happy to present to you the two speakers we could win for this specific AOT, and it's Dr. Herbert Nett from the European Space Agency, and he will turn the tables around, not us from Earth observing the space, no, from space observing the Earth, and what this means and what he does, he will tell you in a couple of minutes. And this will be followed by our very own Miss Universe, Manali Jeste. And if you've been to one of the February events in the pub, you will know that I mean the costume, but I think her beauty also matches. So without further ado, I hand over to Felix, and I wish you a very nice event.
So thank you, Sander, for that great introduction. I am Felix, and I will be your moderator for today. And as Sander already hinted at, we have some exciting science for you today. And yeah, since we had Astronomy on Tap, we have to live up to its name. So I grabbed a beverage of my choice, and I encourage you to do the same. And we can do that until we finally get back to the pub. So cheers to everyone. Great. So our first speaker for today will be Herbert Nett. He studied physics at the University of Bonn, as many of us did, but also myself included. And he did his PhD at the Max Planck Institut for Radioastronomy in the submillimeter group. He then moved to the University of Bremen, to the Institute of Remote Sensing, where he conducted aircraft experiments for stratospheric trace gas measurements. And for the longest time, he has been working now at the European Space Agency, which you probably know, especially at the branch of ESTEC, which is the European Space Research and Technology Center in Noordwijk in the Netherlands. And he more specifically works at the Earth Observation Projects Department. So welcome to the show, Herbert. Can turn on your video and microphone.
Okay, so I hope it works. So thanks you, Felix, a lot for the introduction. And okay, let me just see if I can share my screen as well. Just give me a second.
Yes.
I hope something is coming up.
I can see it. I can see it, yes.
Okay, again, thanks you, Felix, for the introduction. And I must say, I'm very happy to be able to talk to you, to all of you tonight, because I spent really 10 of very fantastic years in Bonn during my studies. And that was the period between 79 and 89, so quite some time ago. But I have really good memories. Just to tell you, at the bottom of my title slide, you see a little crown. It's just to mention to you, as I told Felix and Laila, it's a very important holiday in the Netherlands today, which is the King's Day. So everyone is celebrating. and while we are discussing about Earth observation. So the subject of my presentation is to give you an introduction into the Earth observation program at the European Space Agency, and we will have a closer look at some of the atmospheric missions. So some of the projects where I was personally involved. First of all, what is ESA about? ESA was funded actually in 1975 by 10 member states at that time. Since then, it has been growing fast, and there is a total of 5,000 employees. So something like 2,500 are permanent staff. The other ones are contractors or scientists, visiting scientists. And the idea was at that time to build a European force to explore in a peaceful manner the space, and also to build a European launcher program. In total, there are 7 sites all the way across Europe where ESA is located: headquartered in Paris, a technology center in Holland, operations in Darmstadt, and so forth. And then there is a spaceport in French Guiana in South America. In total, there is a yearly budget nowadays of about 6.5 billion, and this is distributed among the different disciplines, which cover the space science, which includes planetary missions, observatories. Then we have human spaceflight, telecom operations, and satellite navigation. And the fastest growing area is actually the Earth Observation Directorate, which takes about 1/5 or 22% of the overall budget. On the next slide, you see a kind of overview on the different branches in the Earth observation program, where we have, first of all, in light green, the so-called science missions, or scientifically oriented Earth observation missions, which started back in the 1990s with the first and second Earth remote satellite, ERS-1 and 2, followed by ENVISAT, and then a sequence of so-called Earth explorers, which is still continued into the nowadays period. Then we have in the orange color the operational metrology missions, which are done, developed and operated jointly by ESA and EUMETSAT. And then thirdly, we have what we call the so-called Copernicus Program. This is an initiative which was initiated in the late 1990s between the European Union, ESA, EUMETSAT, and the various member states. And this is after to set up, let's say, a data record on data, satellite data on various environmental themes, and particularly on climate relevant topics. So the Copernicus program includes a whole series of so-called Sentinel satellites, which the first of all was launched in the 2015 timeframe, and the program is ongoing at this moment. I will, on the next slides, start to give you an introduction on some of the missions. First of all, on ENVISAT, which is a let's say, payload mission, and we will focus on one of the payloads on that satellite. Then we move on by a big time jump towards the Sentinel-5 precursor. And then last but not least, something in the future, which is the CO2 monitoring mission, which is currently in preparation. Now let's start with ENVISAT. ENVISAT was the first big mission, and it was one of the biggest satellites under development at that time. And it carried a total of 10 payload instruments looking at various aspects, mainly Earth's surface, vegetation, ocean, ice coverage. And 3 of the instruments were looking into the atmosphere. The satellite was developed in the 1990s, and then it was launched in 1st of March 2002 with an Ariane 5. It was the second satellite actually launched with that large launcher. The design period or lifetime was 5 years, and it actually doubled the lifetime. So the operation ceased in 2012. Actually, the Envisat was launched into a sun-synchronous orbit at a height of 800 kilometers and on a polar orbit, which actually allows it to give a real global coverage on the various target parameters. Now we have a look at one of the payload instruments, the atmospheric payload instruments, which is the so-called Michelson Interferometer for passive atmospheric sounding. MIPAS is short. The instrument is mounted on the tip of the satellite, as you can see on the photo here on the left side. Let me maybe put the pointer on.
How big is that satellite?
The satellite is roughly 8 to 9 meters in height. And what you see here, the whole satellite, after integration of all the payloads, is placed in the large solar simulator at ESTEC, which is a big vacuum chamber with a cooled environment. And it allows to do thermal studies, thermal gradients, and thermal cycling studies on the platform and the various payloads. And you see, to compare the size, you see the people climbing here on ropes up and down the satellite. So it's really quite a big satellite. So now the MIPAS instrument was meant to sense Earth LIMP, so-called LIMP spectra, by means of a Fourier transform spectrometer, and to cover the thermal infrared range, which means all the way up from 4.2 micron up to 14.6 micrometers. And what you see here in the sketch is the viewing. It's showing the viewing geometry. LIMP viewing means we are looking tangentially through the atmosphere, and we see, in fact, the atmospheric spectra in emission against the cold deep space background, and allowing, let's say, the instrument to scan throughout the different layers of the atmosphere. We are able to construct vertical profiles on a series of trace gases which are relevant for atmospheric chemistry. And most prominent, it was the ozone chemistry at that time, by the time of the launch of Envisat. So the heart of the instrument is a so-called Michelson Interferometer, which basically consists of a beam splitter and 2 mirrors operating on a linear slide. And this is what the little sketch is showing. As we feed the atmospheric signal, the atmospheric emission spectra, into the spectrometer, we are generating 2 partial beams, and we have 2 output ports of the instrument which produce interferograms which are inverse to each other. In fact, if we had only a monochromatic signal at the input, we would see a sine wave oscillation on each of the output ports. So if we feed the instrument with a real atmospheric spectra, a broadband spectral set of lines, we will see something more complex. And these are some typical examples of real atmospheric interferograms as we obtain them in the different spectral bands. So going from the interferograms to the spectra, there are several corrections and calibration algorithms involved, and mainly it's also the Fourier transformation to transform the data from the interferogram domain into spectra. The big advantage of that technology is that we achieve a very large spectral coverage that I mentioned already, and at the same time we obtain a very high spectral resolution. And we see here a few example spectra. On the left side, we have on the long wavelength edge the CO2 emission lines, which are nicely separated and are part of a strong emission band, which is around 14 micron. Then we have towards shorter wavelength, we have emission features of methane nitric acid and water vapor. And then on yet shorter wavelength, we see additional spectral lines. So the big advantage of the technology is that we are really spectrally separating the emission features, and this allows also to process data in so-called micro windows, spectral micro windows, and to perform the trace gas analysis. And here we see two examples on the left side. This is a vertical cut through a full orbit on covering a height range throughout the stratosphere from 10 to 12 kilometers all the way up to 68 to 70 kilometers. Along the x-axis, we have the orbit position or latitude. On the right-hand side, we see a similar diagram on the ozone distribution. So you see clearly the maximum of the ozone in the 35 to 40 kilometer area. And also you see near the North Pole a minimum of the ozone part. It's actually what you see here. This corresponds to the South Pole. This is not an ozone hole, but it's actually a data gap which is linked to the observation geometry and the orbit inclination. So far on Envisat. Now we make a jump forward in time by some 15 years, and we come to the Sentinel-5 precursor mission, which is actually the first atmospheric mission within the Copernicus program. The idea is here to focus on the chemical composition of the lower atmosphere, troposphere, lower stratosphere, and to focus on air quality and climate monitoring. Compared to similar instruments on metrology satellites, this mission provides significantly enhanced radiometric sensitivity and spatial resolution, and you will see an example in a moment. The satellite was actually launched in October 2017 by a Russian rocket launcher. The launch mass is quite exactly 1/10 of that of Envisat, just to give you an idea for the sizing. The payload consists of a single instrument, the so-called Tropospheric, and the mission duration design-wise is 7 years. So it's actually measuring at this time. Again, this satellite is on a near polar and sun synchronous orbit at a height of 824 kilometers. In contrast to the limb geometry that we had for MIPAS on Envisat, we are looking at the backscattered solar light from the atmosphere. So we are really relying on the solar irradiance impacting the atmosphere, and then we will see scattered lights and absorption features at the various layers in the atmosphere. And the longest in the extreme path, the beam goes all the way through the atmosphere, hits the ground, and is then scattered back by means of the surface albedo. And we are actually seeing the twice the passage through the atmosphere. This method is a very accurate one to obtain total column measurements of trace gases. The instrument onboard S5P, Sentinel-5P, is the tropospheric monitoring instrument, which is actually a grating spectrometer operating in a total of 8 different bands, ranging from the UV all the way up to the shortwave infrared at 2 micron. It's using a so-called push boom measurement geometry with a very wide swath, about 108 degrees cross track. The instrument was mostly developed by the Dutch Space Office with the constructor Airbus Defense and Space, located in Leiden in the Netherlands. The satellite and the sphere module was actually provided by ESA. So there were quite some innovative elements on the instrument, including a free-form telescope, allowing this very large viewing angle range. Another one is the use of a so-called immerse grating, which is a combination of a reflective grating with a prism, which generates actually a very high spectral dispersion or angular dispersion to allow the instrument to be built in a very compact way. Now, the instrument itself is shown here in a sketch. I don't want to go into details, but one of the main elements is the radiant cooler, which is actually used to cool down the optics for the infrared part and the detectors themselves. And here you see a mock-up in a folded configuration before installation on the satellite. What I'm showing you here is a kind of sketch of the orbit viewing geometry. Sentinel-5P is actually flying in loose formation with an American satellite called Suomi NPP. I will launch a movie here. So what you see is Sentinel-5P is following 5 minutes with a 5 minutes distance the Suomi NPP. Both satellites match in their swath quite accurately. And what you see also on the near the equator, that we see adjacent swath. That means we are actually obtaining a full global coverage of the two satellites. Another element is, by the way, what means a sun-synchronous orbit. If we look at the distance between the satellite at the equator crossing and the day-night terminator line, that this is a constant one. So this means, in fact, that the orbit plane has a fixed orientation towards the sun direction. Okay, let's move on to some interesting results. We have here, first of all, this was 6 weeks after the launch, actually, in October 17, a breakout, the eruption of the Mount Agung on Bali, Indonesia. And what we have here on board the metrology satellite METOP measurements by the GOME 2 instrument of sulfur dioxide. So there was a large, let's say, blowout of volcanic ashes, but also sulfur dioxide. And here you see the measurements by the METOP satellite. Now, on the same day, with a slight time difference, we also had an overpass of Tropomi, where you see the effect of the much higher spatial resolution. Remember the 7 by 7 kilometers compared to the 80 by 40 kilometers of the GOME instrument. So you see that the contours of the plume, of the gas plume, are much better let's say pronounced, and also you see a much better dynamics in the signal. I think this is something that you might also observe in astronomy applications. Another example is measurements of NO2. Nitrogen dioxide is actually produced whenever we have high temperature burning processes of fossil fuels, such as coal-driven power plants, steel factories, or diesel engines. And you see in the area of China quite high levels of pollution. And what we see here is a period, a kind of animation over a period of 4 months from December 19 through March 20, which covers actually the period when the coronavirus turned up. So you see, first of all, we start at these high levels, and as we move into January, February, you see the effect of the industry lockdown in China. And you see we are strongly reducing the NO2 emissions, which is actually the effect of closing down the factories and power plants to a large extent. And then as the restrictions are lifted towards end of February, we see that the pollution levels are returning or are coming back towards the previous levels. So far on the records on Sentinel-5P. We have a quick look into the future. The good news is that the European Commission has recently released the budget for a whole series of new generation Sentinel missions, which will look into several themes on Earth observation, such as polar ice coverage, sea surface, ice concentration measurements, agriculture, vegetation analysis, and also soil and biodiversity missions by means of hyperspectral imaging. So there's quite a number of technologies ranging over several spectral ranges, and also including SAR, synthetic aperture radar measurements. But first of all, the priority is given to the so-called anthropogenic CO2 monitoring mission, which I mentioned in the beginning. And this is meant to monitor the man-made emissions of CO2 and also methane over a longer period. And this project was actually launched in mid-2020, the industry contract to start building the satellites and the various payloads. And this follows also some preparatory studies which have been ongoing for quite a couple of years under the lead of ESA. And this mission is put in place in response to recommendations that were given at the COP21 climate conference in Paris in 2015. So we are very happy that, let's say, the budget of this mission and also of the other missions is basically secured. And in the case of the CO2M mission, we are aiming at a 3-satellite constellation and to provide first data in the 2025-2026 period. The idea is to also provide data for a first global stocktake of anthropogenic CO2 emissions in 26, around 2026, and then to repeat such a stocktake in 5 years intervals. And this is really meant to measure, to have a quantification of the policy making and to see the effects of political decisions and CO2 emission restrictions. So that's all I wanted to say about Earth observation. This slide is introducing a bit the job opportunities at ESA. In fact, at ESA, people work in various disciplines on engineering, science, IT, software development, but also on laws and contract management, and even in natural and social sciences. So this is also reflected in a kind of support program for young graduates coming fresh from university. And this is, first of all, the so-called Young Graduate Trainee Program, the YGT program, which is basically a job opportunity for people who have fresh graduated or achieved their master degree and to work in the various disciplines offered by ESA. Typically, such a contract is given out for 1 year plus an optional extension by another year. On top of that, we have the so-called national trainee program. So several countries, as you see here, Belgium, Estonia, Germany, and so on, place extra budget on ESA to create extra job opportunities on specific areas. In addition, we have also for postdocs or people who have just achieved their doctorate, the so-called research fellowship program. And this is to allow to conduct scientific programs over periods of 2 years. So that's the contract duration, again, with an optional extension by 1 year. And then last but not least, and this is more a bit of exotic area, this is co-funded research activities. So in case there are space-related PhD projects, also with a link to industry, then also ESA may engage in supporting such projects. And this is also to build the bridge between, let's say, universities, research institutes, and industry. So far on the job opportunities, I have here a couple of links about the career opportunities, but also on the Earth observation program in general and data access and so forth that you may want to consult if you are further interested in the ESA work. So thank you all for your attention. So I'm happy to answer any questions.
Thank you very much, Herbert. This has been very interesting. And I guess if people want to have those links, we can also like post them, give them to you later if you ask for them. And this is your opportunity to ask more questions. I think also if you are interested in a job at ESA, I think Herbert is also a good person to ask, and also now's your chance. We have one question so far from the chat. It reads, can the Fourier transformation be done once the data is received from the satellite rather than placing the spectrometer on the satellite?
I'm not sure if I understand this. Is this about the conducting the data processing on board rather than downlinking the raw interferograms?
I think that's what they're asking. Yeah.
Okay. Yeah. Now, the idea is, first of all, the data are normally downlinked as pure and as raw as possible. And this is also to have enhanced, let's say, opportunities to check the instrument health. So, for instance, if we would directly perform the fast Fourier transformation on board, this could be done, and you could also reduce the data rate a lot. But then you do not have the same ways of diagnosing the detector performance. For instance, when you have spikes in the interferogram due to cosmic radiation, or you have a degradation of a detector and you change the nonlinearity response curve, then this is better or easier to correct on ground based on the raw interferograms. But I must say, in the future, when you go from, let's say, single point, because MIPAS was, it's quite old technology. It had only a single measurement point, but in the future, there's also the idea to go to 2D imaging, that we are looking in the azimuth and vertical direction at the same time, and then acquire the interferograms. But then, of course, the data rate will explode, and then you might be forced to really perform a lot of data processing on board and downlink the calibrated spectra. But it was not done at that time on Envisat, because it was a novel instrument, and one wanted to be on the safe side. We keep the data as raw as possible.
Okay, I think that probably answered the question. Actually, I have like some questions myself, and first, I could say that it's really interesting to see this kind of perspective for me as an astronomer who always likes to observe through the atmosphere some objects on the sky, and now we have the other way around to observe the atmosphere, which is normally for us astronomers just a hassle. So I have been observing last weekend, and I can say, although we had pretty good weather at that weekend, it can be different, and it's really just our way. But in fact, we can learn very important things from observing the atmosphere, like you said, with the climate change monitoring of CO2 levels and other important traces, right? There's one question that I have to that. I mean, you also think you have some resolution, like in depth of the atmosphere. Like, where in the atmosphere do you actually find the CO2, for example? Is it like in the outer layers of the atmosphere where it reflects the sunlight, or is it like distributed differently?
Yeah, the CO2 is a special case. It's very well distributed, and you will see it all the way up from the ground up to 100 kilometers height, and it's globally very well mixed. The problem is, in fact, that the CO2 is a very stable molecule, and it lasts in the atmosphere. It has a lifetime of around 100 years. So once you generate a CO2 molecule and you emit it into the atmosphere, it will stay. So that means the measurements that you do are basically total column measurements of the through the atmosphere, with the two-way optical path, as you have seen. The problem is, if you want to measure emissions, it's very difficult because the emission is only at the very at the lowest level in the atmosphere. So that means you have, let's say, a power plant with the emission of CO2, then you have an enhanced level of CO2 at that area. But soon after, the CO2 will diffuse and it will distribute all around the globe. And actually, I mean, we didn't dive very deep into the data processing, but one very important element is for the CO2 emission is that you measure NO2 at the same time. The NO2 has the advantage that it's an unstable molecule and it lasts only for a short period. And that's also why you saw in China these high elevated column amounts on NO2. It's because the plumes don't last long. The NO2 is stable for about 24 hours or a couple of days at most. So that means the NO2, it's produced in a fixed ratio with the CO2. It depends on the temperature of the burning process, and then you can use the NO2 as a tracer to locate the elevated CO2 areas. So in fact, the CO2 to measure is not very difficult because there's lots of emission features because it's a greenhouse gas. That's why it's very active. That's why you can measure it in the infrared. But the problem is you want to measure very small incremental changes in the CO2. Since you are looking through a big column of, let's say, 100 kilometer thickness, and you see only a change at the very lowest layer in the atmosphere, the percentage change is a fraction of a percent. So you may see an enhancement of just 0.1%, although because you are averaging the overall column. So that's why in the data processing, you use at the same time measurements of NO2, which will give you the contours of the exhaust plume, which is linked to the wind direction, wind speed, and so forth. And you can nicely find the contours of integrating the CO2 emissions. So it's quite a tricky way of processing, and it's really challenging in terms of instrument performance and also the data processing.
I see. I understand now. So basically, the NO2 acts like sort of as a tracer for the CO2 when it's emitted. This actually reminds me that we use, like, for example, a similar technique in astronomy where we actually use CO2 as a passive tracer for hydrogen, for molecular hydrogen, which is a sort of different principle, but it's the other way around because we use CO2. Okay, now. Let's move on in the interest of time. So thank you very much again, Herbert, for this very interesting perspective on Earth observations.
Okay, thank you.
Okay, let us move on to our second speaker, which is our very own Manali Jeste. She obtained her bachelor's degree in physics from Ferguson College in Pune in 2015 and joined then the University of Bonn for her master's degree in astrophysics. So we have another alumni from the University of Bonn. So since 2019, she is working on the PhD project in the submillimeter group of Professor Menton, also at the Max Planck Institut for Radioastronomy, where she works on the Large Program Atomium, where she traces the origins of molecules which form dust in oxygen-rich mirrors. So welcome, Manali.
Hi, thank you for the kind introduction. So I will share my screen. Can you see it now?
I can see it well, okay. Yeah.
Thank you. So yes, so today I will try to give you a story of dying stars. So how these basically explain the life of stars, which are almost closer to their death, so to say. So I will take a step back and talk to you about what is a star. So this is basically an astronomical object which is radiating its own energy and is bound together by gravity. So how are these stars formed? Basically, what happens is that there is a gravitational collapse happening in the molecular clouds. So these clouds are gaseous region in the interstellar space where they are quite dense, they are quite cold, they have a lot of molecular hydrogen. And this leads to a gravitational collapse happening in these regions. So on the right, I have shown one of the famous star-forming regions, which is the Eagle Nebula. So you can see the nice eagle-shaped nebula, which and it also has this pillars of creation, which I'm pretty sure everyone has seen. So this region has a lot of stars, and it is produces around thousands of. It's responsible for production of thousands of stars, and so all of the stars have different masses, and when they have different masses, they are actually already these masses are already deciding the fate of their life. So when I say that, we actually do classify them based on their masses. So here, for an example, we have massive stars. So massive stars are the stars which have masses of more than 8 times the mass of the sun. So, so one of the most famous ones is the Beetlejuice, which you have heard because it got very popular. It had a lot of dimming, and then it got bright again. So what we have here is the red supergiant, it's called, and it's Beetlejuice. So this star or this type of stars would later, after quite some time, would explode in the form of supernova. And then what would be left is a black hole or a neutron star. Again, it depends on the mass that the star would have. So here what I've shown is actually quite a simplistic way of the evolution of the stars. So there are a lot of different evolutionary phases that go through, but just for the simplistic view, I'm only showing the representative parts of the evolutionary phases. But today I will just give you a view of the low mass stars, so the low to intermediate mass. So they have masses of less than 8 solar masses. What we have in the beginning here are already in the later evolutionary phases of the star. So we have here red giant, not a supergiant, but a giant. Then we have planetary nebula, which you all have seen. There are these beautiful images. And then what the star, after expelling some gas in the form of planetary nebula, is left with is a white dwarf. And so this is what I will walk you through. So before going to the dying phases, what the star does most of its life is it is using its energy in the form of producing its energy in the form of nuclear fusion. So these are the stars which are called main sequence stars. So the stars are the energy that is being the molecules that has been in the stars from the molecular cloud, say molecular hydrogen, is being fusing together to form helium. So this process is creating energy, and that is what is giving the energy to the star. And the stars are spending most of their lives doing this. When I say most of their lives, that is billions of years. So on the bottom, I put here a timeline of sorts. So the purple shows you the 10 billion is representative of 10 billion years where the stars are burning this hydrogen. They're fusing the hydrogen to form helium. So that is what our sun is doing right now. So our sun has an age of 4.6 billion years, which would be somewhere here, and it still has more than 5 billion years to keep burning the hydrogen. So you can see how much time it is spending just in one phase. So what happens next after it has been done with the 10 billion years is that it becomes a red giant. So when I say red giant is when previously it was burning hydrogen, but at some point the hydrogen runs out. So what happens in the center, in the core of the star, is that it starts to contract. There is no hydrogen present. And whatever is left is then spread out in a shell form around the core. And when the core is contracting, it is heating up. And because of this heat and the shell fusion, it starts to expand. So it expands so much that it is almost 10 to 100 times that of the sun. It gets really big in size, and also it gets very luminous. These stars are also the ones which have quite cooler temperature. So when I say cool, it's around 4,000 Kelvin. And these stars then appear as redder to us, and that's why we call them red giant. And this is what is going to happen to our sun in about 5 billion years. It will become 1,000 times more luminous than what it is now, and it will also become as big that it will almost swallow us. That you have also probably seen in all the news that it will happen at some point in its life. So, keeping up with our timeline here, you can see how much where we are right now. So it is already so much close to its end of its life. So what it is doing is here around 2 to 3 billion years it's spending as a red giant, fusing the hydrogen to form helium. So helium. And what happens after is that it becomes an AGB star. So what has happened now is that the helium is running out. So you can see how the fuel is slowly running out, and it is trying to produce different elements. So hydrogen to helium, helium to now it starts to produce carbon and oxygen. So now it has these heavier elements in the center of the star. So these stars are bigger, and because of its bigger size, they have a lot of material in the center, and it is starting to pull away from the star. Because of the gravitational pull, it is easier because it's bigger for it to pushed off. So this material is in the form of gas and dust, and what we term it as this material being pushed off, we call it as mass loss. So it's losing its mass, and it loses its mass, and an envelope of this mass is formed around the star. So this is one of the specialty of these type of stars. So they have around also radius of 200 solar radius. So they are quite big, and luminosity is quite high. So around 58,000 times of the solar luminosity, and they are almost the same temperature, 3,000 to 4,000 Kelvin. But the stars are not in this phase for that long as it was before. So this is, you can see here, they are only here for quite a small fraction of time. Slowly they are losing all this. You can see how inefficient this star is becoming in producing more fuel to use it as energy. So this is about 1 million years or so where the AGB star phase lasts. What we have next in these stars is something special. It's called stellar winds. So whatever the gas and dust, the material that is being pushed off, it is in a form of wind. So that it's losing a lot of mass in this form. And when I say a lot, it's like 40 to 50% of its total mass is being lost. So on the right is one of these famous stars, an AGB star. It's called CW Leo. And in the center, you can see that there is a star. And I'm sorry, and there is a star, and then how the material that is coming out of the star is interacting with its surroundings. So we have the interstellar medium, which is again made of different molecules, different gas, dust, or whatever, and this material is interacting with it, and also the star is moving from, let's say, from right to left. It is moving, so it's also getting pushed. So you can see a bow shock that is being formed here. You can actually trace the motion of the gas with motion of the star by seeing by studying the gas. So that is what some of us actually study. We are studying the gas, the molecules that are present in this matter that is being shed from the star. So when I say molecules, there could be any molecules as simple as Felix said, there could be CO or hydrogen, but we use, as he said, that we use CO as a tracer for hydrogen, or it could be very complex. They could go as very complex organic molecules, and they all tell you different stories. So when you study these gas, we study different properties of the gas around the star. So if I say temperature, and you get a hotter temperature, so it means that the gas is tracing the region which is much closer to the star because it's hotter closer to the star. So this kind of information you can get from studying the stellar winds of these stars. And what also is important is this mass loss. So this mass loss is it's very high, so to say, for these stars. So we study that, and when it is losing this mass, it is mixing the molecules in its material around in the interstellar material, in this interstellar medium. And there is all, so this leads to production of molecular clouds, and this would again lead to production of stars. So what it is saying is that we are made of star stuff. So that is what the saying comes from, because that the stars are losing more mass, they're providing for more stars, and it provides for planets, and that's how the life comes into play. So what other properties the stellar winds have are that they are different shapes. So that you can also study, trace from studying the gas around the star. So here is an example of RX Relay. It's one of those AGB stars, and you can see how the wind is behaving here. It is not circular, it's not spherical, it's rose-like shape. So in this case, this star is showing such a stellar wind because there is a companion present close to it. So there could be a star or a planet that is interacting with this star, and because of the gravitational interaction, the shape of the star is changing. The shape of the wind is changing. And this is actually what is influencing its next stage of the evolution. So
this looks beautiful.
Yeah,
actually.
Yeah. And yeah, so the one in the bottom is also my one of my favorites now, is the Myra, and it's also one of the AGB stars. And you can see the star is on the right, and how such a big tail is being observed, and it's because this star is losing so much mass, and it also has a very high velocity. So it's 130 kilometers per second. So it's going very fast through the interstellar medium. So this gas is interacting with the surrounding, and you can see the trace of it. So this is actually, so you can, by studying this, you can find that this star was here 30,000 years ago. So this gas is that old. And how that you can actually trace the motion of the star by studying these kind of winds. And these winds are actually then influencing the next part of its life, which you know as these beautiful images of planetary nebula. So as I said, that these stars are losing a lot of mass, a lot of material, and what is left in the center is an exposed core. So this core is quite hot, and it's radiating in the UV. So when it is radiating in the UV, it starts to ionize the material that is being lost. So it starts to ionize this gas. And that is what we see here with these nice images that we get from Butterfly Nebula or Helix Nebula, as you can see, is because of this process. So these objects have almost the same luminosity as the previous ones, but they are much hotter. And they are quite big, as you can see on Helix Nebula is as big as 4 light years across the size. But their lifetime is much smaller. So here, looking at our scale again, we have here it's spending only 10,000 years of its life being planetary nebula. So you can see how slowly the star is dying. It spent so much time on the hydrogen burning phase, and slowly it is just spending it's going quickly through its phases. What is left in the end is what we call a white dwarf. So when it has lost all of its atmosphere, and what is left in this middle is the compact object. And this object is quite massive. So it's mass as big as the sun, but it is small. So the size it's as small as the Earth. So on the right here is just an artistic impression of a white dwarf. But on the left, you can see that there is an observational picture of the Sirius star. The Sirius is the one of the brightest stars that you can see in the sky. And Sirius A is the one in the center, and this one on the companion is the white dwarf called Sirius B, and it is actually optically 10,000 times dimmer than Sirius A. So this Sirius B is actually only of the mass of the sun, and it is even smaller than the Earth. So it's even 90% of the Earth. So you can see how dense, how compact this object is, and its gravity is 400,000 times than what it is, what we have here. So it is quite compact, a dense object and hot object. And this white dwarf, this object is formed around 75,000 years after losing all of its ionized gas. And what it does is that it takes really long time to cool down. So when I say long time, is really long. That is more than 8 billion years it would take to just start cooling down. What happens is that it's cooling down, and it tries to get the same temperature as its surroundings, very low temperature. But and what we get is a black dwarf. But because it takes so long and for it to cool, we don't have any observations of this kind of dwarf because our universe is not that old. It's not old enough, and which is what brings us to my conclusion, and that is that the old life of the stars is quite different than what we have. So we are more fun. We are doing many things and more adventures when we are young, but we are quite quiet in the end. But the stars are the exact opposite. They're quite quiet. They're very calm in the most of their lives, but then they're so much different. They're going through evolutionary phases so quick, and they're giving us such beautiful images in astronomy, like planetary nebula, and it's very quick and going out with a very lasting mark on all of us. So this concludes my talk.
Okay, thank you very much, Manali. This was again very interesting. Feel free to ask questions in the chat. Otherwise, I will just ask my questions. Exactly the picture that you're showing here, I find it very interesting. These ejecta from the stars, they extend like to very large sizes, right? Like how large is this one in terms of light years or something?
Yeah, it's 13 light years, so it's quite big, 13.
And this specific one, it sort of traces the motion of the star, right?
Yeah, this specific one, this whole length is 13 light years apparently.
Yeah, I find it really interesting how small these stars actually are, and I believe the other object that we can see here are stars, but they can have like such a large trail that they leave behind that we can actually observe.
I mean, this one is quite exceptional because I think they were not looking for this star, and suddenly when they found it in the images, they were also surprised. So this was not a planned observation of the star, apparently.
Yes. Actually, that you mentioned the black dwarfs. I guess if they really cool down to such a degree that they are black, we could not observe them anyway, right? In that case, they're similar as black holes in that sense. That
True. It would be again illustration rather.
But maybe we can trace them by passive means, like we do with black holes, like with the orbits of other stars or something, right?
Yes, but I guess not in our lifetime.
All right. Okay, I think there are no further questions. So thank you again, Manali, for this very exciting talk. And thank you. And we can finally move on to the answers of the quiz that you hopefully were very ambitious about and tried to really answer it thoroughly. So I hand over to Sandra now, and I see you next time again.
Thank you very much, Felix. And I'm back this time with the quiz because our other poor quiz master is on his way to his girlfriend, and we really wish him a good vacation. So you have to see more from me today. And in the quiz, as you know, we try to sneak some knowledge into your brains by making you either Google it or you know it already. And then we start with the Astro News. There was something that is not spinning quite right. And this discovery could turn physics upside down. We are talking about. So this one is really interesting. These things are called muons. Muons are like the cousin of the electron, like the heavier part. They're 200 more times heavier than an electron, and electrons you might know. And people now have measured at the Fermilab, the Fermi National Accelerator Laboratory, that it does not behave as we expect it to be. And we physicists love these things because we have a standard model, we have calculations, we know how this thing should move, but we can now prove that it does not move as expected. And this always hints to new physics, so that our standard model is actually not complete. There are always some hints. And here we have a proven hint. You may think maybe it's just coincidence, the measurement. I think not, because it would be a coincidence of 1 to 40,000. This is how precise they have measured it. Yeah, so this makes physicists always excited. And what you can here see are the cute plushies from the particle zoo. And I'm very happy that I could finally sneak some advertisement for that into here. The second question is, Ingenuity achieved another milestone. We now performed on Mars. So this is not a game of cards against humanity. So we give you a proper answer, and the answer is it's some helicopter flight or something that needs a propeller. And the small drone was attached to Perseverance, which landed just recently. And it's a technology demonstration to test powered flight on another world, on another planet for the first time ever, which is extremely challenging because the Mars atmosphere is actually very, very, very thin. And for people of you who know a bit about helicopters, they should know that they need some kind of air cushion below their propeller to actually move up. So if you have a thin atmosphere, this gets more challenging. But by now we have the third flight from this little drone and the first true color picture from the Mars surface. That brings us to the third and last Astro News. So scientists were skeptical, but experiments seem to show that a very futuristic propulsion method might work in space. Now those hopes are crushed. And what we are talking about the so-called EM drive or M drive or Q drive or RF resonant cavity or the impossible drive. You may have heard about this term in the last, I think 20 years ago. It was actually proposed that this might work. It's a very curious box filled with microwaves that just bounce around in this box. And it's a groundbreaking and physics-defying revolution in space travel. At least this is how it was announced. However, it also defies some laws in physics. So if this thing would work, that would also mean we have not understood physics as well as we think we do. However, now physicists in Germany have showed that you cannot actually get any propulsion, any thrust using this method. Conservation of momentum is what prevents it, which basically means in layman's terms, you need to push off something to actually move, and just some photons inside a box won't do that. As you may have guessed from just hearing it the first time. But there were some experiments in the past which claimed that there is some propulsion, but now these have been refuted. So that brings us to the next section, which is some Pictionaries. We have famous astronomers and artists that we ask to provide a picture, and you have to guess what it is. And this here is not a honeycomb for space bees. This is a picture of the mirrors from the James Webb Space Telescope, which is a successor of the very famous Hubble Space Telescope. It's a collaboration of NASA, ESA, that we just had a visitor from, then the CSA, which is the Canadian Space Agency. And, we are very, very excited that this thing might launch soon. So the new date is end of October this year. And it will give us far better images than Hubble. You have to imagine the technology that Hubble uses is so old, any smartphone in space would probably beat the Hubble Space Telescope. But, it was designed to launch in 2007. We have 2021 now. And I know that there's some open bets when this thing will actually launch. So, fingers crossed. And by the way, the yellow color is some gold-plated beryllium. So whenever you see this honeycomb, now know that this is just the next optical space telescope that will probably give us very, very, very pretty images of galaxies out there. So the second picture is this one. I think you probably could guess that at first glance. It is a very, very good advertisement project from the company SpaceX. It's some car in space, no further advertisement here from us. But I really think it's a good drawn picture, at least. I couldn't. I'm not very talented. Third picture is this one. So also something with Earth, but this time definitely not a car. What you should get a hint from this picture is the so-called ETA Accuride meteor shower, which is expected around 5th, 6th of May to peak with 50 meteors per hour. So if the weather stays like this and you have a night which is kind of clear, 50 meteors per hour, you don't have to wait a bit more than a minute on average. And it's actually the debris trail from the iconic Halley's Comet. And actually, the Earth passes through it twice a year, with the second coming in fall with the Orion night meteor shower. So if you don't have anything better to do, I think that's something that we can do with the current restrictions. Last for today is we now have a new category about some famous astronomers and what they actually discovered. And we gave you this beautiful panel of 9 very, very famous astronomers. Each single one of them distinguished astronomer. And then we gave you some discoveries, for example, who measured the circumference of the Earth using shadows. You could either give the number, or if you know the name, you can give the name. We were hoping this is a bit fun. And the number for this one, who was the first one to measure this, was I tried to pronounce that name before that I don't stumble at this exact point. Okay, just read it, Greek name. He's a mathematician, he's been a geographer, poet, astronomer, music theorist, and also the chief librarian of the Library of Alexandria, some 200 BC. And the Earth's circumference was not his only achievement. He also measured the tilt of the Earth's axis, and more great discoveries already more than 2,000 years ago. And we're just rediscovering some of them in the past 100 of years. So the second discovery is who discovered that stars and thus the universe are mainly made out of hydrogen. So the answer to this is Cecilia Helena Payne-Gaposchkin in later years. She lived some 100 years ago, and her research led to the thing we now know as star classification, to the very famous Hertzsprung-Russell diagram, if you've ever heard of that. And unfortunately, she never really got the credit for her work. So that was part of her PhD thesis, which was groundbreaking because it contradicted everything they knew so far. But she was convinced by her supervisor that she shouldn't put it in a very rigorous way down because it would contradict current research. But still, she was the first, and the credit is due. And then the last discovery for today, who calculated the orbit of a comet and predicted its appearance? Yep, there was already a hint earlier in the quiz. It's Edmund Haley, which is the first picture here in our 9 panels. And he lived in the 17th century, and he used, what we nowadays think is quite simple with respect to other things, just the laws of motion. With that, he predicted the periodicity of the comet. It wasn't named Halley's Comet back then. It was only named when this very comet returned, which Halley unfortunately didn't even see. And after that, it was renamed as the Comet of Halley. So that was for the quiz. And we always have some prizes for you. You win if you have more than half of the answers right. If you're lucky enough to be one of the 3 randomly drawn winners. And if you actually did put the valid email address, because otherwise we cannot contact you to get your address. and then ship all those packages to you. Due to the lockdown, this now takes a couple of weeks, so be patient with us. We are sorry for any inconvenience. And what you can win, it's either a book by Stephen Hawking or some quiz or some little metal thingy building kit. Or if you're here situated in Bonn, you can also get some Tai Chi lessons whenever it's possible again. So that was me as the quizmaster, and now change back to giving some outro last minute of the event. Thank you very much for listening. I had a lot of fun. I learned a lot about Earth observations because I'm not very good at that maybe yet. Maybe I changed profession, who knows? And we see each other again at the 25th of May. Mark it in your calendar, 7 p.m. And we will announce at the social media who's giving the talks then. So